Hello, students. This is another endeavor by me to look for something more challenging, physics-wise. And I found the entrance exam questions, the engineering and medical entrance exam questions of India. These questions are so challenging. Now, this becomes more challenging because of many reasons. Number one, 72 questions in physics, plus 48 questions of chemistry, which makes 120 questions, is to be worked out in 120 minutes. Yes, you heard me right. So that means for each question, you only have 1 minute. If that is not challenging by itself, you do not have a formula sheet. So you got to have all the formulas in your head and the concepts. You got to remember all that. So you're not given a formula sheet. Number three, neither are you given a calculator. So this is what makes it so challenging. So number one, you got to have all the concepts and formulas at your fingertips. Number two, you need to know how to solve them mathematically without using a calculator. And then you got to do as many questions as possible. And in this entrance exam, there's also negative scores. So if you get a question wrong, then you get -1. But if you get a question right, you get +4. Well, that's something positive, correct? But still, the negative stops the students from guessing out. And so this is where we're starting out on our journey. And I hope to work out many questions. So I'm starting with the questions from 2014. And I'm going to try to give you as much theory as possible and try to get you to the answer as quickly as possible. All right, so I'll give you the shortcut methods, I'll explain the concepts in full, and hopefully this will be really useful for you. So let's get started. All right, question number one, 5 cells, each of EMF E and internal resistance R, send the same amount of current through an external resistance caps R, whether the cells are connected in parallel or in series. So you have 5 cells, each one has an EMF E and an internal resistance little r, and they send the same amount of current through an external resistance caps R, whether they are connected in series or in parallel. So now you got to know how to connect the cells in series and in parallel. Well, when the cells are connected in series, the total EMF becomes 5E. And the total internal resistance becomes 5R. Okay, so that with the external resistance will make the total 5R, 5 little r plus caps R. And the total EMF is 5 times E. Therefore, by Ohm's law, the current would be 5E divided by this total resistance. I'm going to show you in a minute. But without writing it, I'm trying to give you the idea. When in parallel, what is the total EMF of these 5 cells? Each one has an EMF E, but in parallel, the total EMF is just equal to the EMF of one cell. So that means it will only be E. So whether you connect 5 or 50 or 500 cells in parallel, as long as they all have the same EMF, the total EMF is just going to be E. Very important point. And what about the total internal resistance? The total internal resistance becomes R by 5, little r by 5, which when combined with the external resistance is R by 5 plus caps R. And then the current would be E divided by R by 5 plus R. And we set them equal to each other and solve. So here we go. In series, I is, you see the circuit diagram now, I is 5E by R plus 5R. All right, you see the cells connected in series. And in parallel, the current is E by R by 5 plus R, caps R. That becomes 5E by R plus 5R when you take the LCM. And then, when you set them equal to each other, the numerator is, of course, going to get cancelled out. So 5e cancels out. That means these two are equal to each other. And then rearrange, bring the caps R terms to one side and the little r to the other side, and you get R by R is equal to 1. So voila. So you get the answer. See how many concepts you had to know there, okay? Let's move to the second one. In the second one, the power dissipated in the transmission cables carrying current I and voltage V is inversely proportional to. We know that before you transmit power over cables, you have excuse me, you have a transformer, you have a step-up transformer, because the voltage on the secondary is going to be higher while the current will be smaller. And so the small current at a big voltage is being transmitted on the lines. Why do we need to have a small current? Because the heat produced, which is how power is dissipated, is given by I squared R. See, I squared. So if I is small, then you can reduce the amount of power dissipated. So that's the idea. You have to start with power is equal to VI, from which you get I is equal to P by V. And then power loss or power dissipated is I squared R, where little r is the resistance of the transmission cables. But we can now substitute for I as P by V, which gives P squared by V squared. And then we know that P squared is a constant because you want to transmit a definite power, and also little r, which is the resistance of the transmission lines, as a constant, which leaves V squared, and that's in the denominator. So that means power dissipated is inversely proportional to the square of the voltage. So that must be clear from there, right? Power loss is inversely proportional to V squared. That means if you transmit power at a very high voltage, then the power dissipated will be small. That's why we need a step-up transformer before transmission of power is done. Got it? Number 3, a rigid container with thermally insulated walls contains a gas and a coil of resistance 50 ohms carrying a current of 1 ampere. The change in internal energy of the gas after 2 minutes will be. So it's a rigid container and it's thermally insulated walls. That means no heat is lost. And you have a gas inside, a coil of resistance 50 ohms carrying current 1 ampere. So how much heat would that produce? We can use I squared R to find out the heat produced, and all of those heat. But remember, that's the heat produced in 1 second. I squared R is the power dissipated, which means heat produced in 1 second. So therefore, you can calculate the power dissipated in 2 minutes, because 2 minutes is 120 seconds. So multiply it with 120 and you would get the answer. So this kind of question, can be done in 30 seconds, right? Or 1 minute. So that's where you save some time. So I squared R gives you 50 watts, which is joule per second. And then 2 minutes, you get 50 times 120. That gives you 6,000 joules, which is 6 kilojoules. 6 kilojoules. Number 4, about magnetic field now. The magnitude of the magnetic field inside a long solenoid is increased by. So now we need to know the formula for a magnetic field inside a long solenoid. What is it? It's B is equal to mu naught Ni by the length. So first of all, we're not talking about magnetic flux. We're talking about magnetic field. Flux is different. Flux is magnetic field multiplied by area of cross section. So here we see that the magnetic field will not depend on the area of cross section, because we're talking about magnetic field, not magnetic flux. And magnetic field is given by mu naught Ni by the length. So if we increase the number of turns, you can increase. All right, again, mu, I'm going to show you how we get that. Mu is actually mu naught times mu r, because remember, mu naught is the permeability of free space or air, but instead, if you put an iron core, like bundle of iron wires, then you increase the permeability, because iron is a ferromagnetic material. So relative permeability of iron is mu r. It shows how many times it has a permeability more than that of air. So to get the actual permeability, you got to multiply the permeability of free space with that of the material you have put in. Okay? And then caps N is the number of turns, total number of turns. I is the current, and L is the length. So if you look at A, decreasing its radius, well, magnetic field has nothing to do with radius. Decreasing the current through it, if you decrease the current, then you're going to decrease the magnetic field. So that's wrong. Increasing its area of cross-section, I already told you, magnetic field does not depend on the area of cross-section, but magnetic flux depends. Here, the question is about magnetic field, so it does not depend. Decreasing the number of turns, look at that. If you decrease the number of turns, then the magnetic field is going to decrease. Therefore, the correct answer is introducing a medium of higher permeability. That means increasing mu r. So when you increase mu r, you're going to increase the magnetic field on the axis of a solenoid. So I hope that makes sense. Number 5, a bar magnet of moment of inertia, that means rotational inertia, 9 times 10 to the negative 5 kilogram meter squared, placed in a vibration magnetometer and oscillating in a uniform magnetic field, 16 pi squared times 10 to the negative 5 Tesla, makes 20 oscillations in 15 seconds. We have to find the magnetic moment of the bar magnet. So now we need to know the formula for time period of oscillations of a magnet in a magnetic field. You have a suspended magnet in a magnetic field, and if you just disturb it, it's going to oscillate. And the time period of oscillation is given by 2 pi square root I by mb, where I is the rotational inertia. Let me show you that. 2 pi square root I, that's rotational inertia, by mu b. Okay, I'm using mu. Mu is the magnetic moment, which is what we're trying to find. So make that the subject, right? So square both sides in order to get this, get rid of the square root, then make mu the subject. You're going to get 4 pi squared by t squared, I by b, and which is 4 pi squared. Now I is given. And then you have to look at what is t, what is the time period? 20 oscillations in 15 seconds. Now don't go wrong there. So what's the time taken for one oscillation? One oscillation, 15 by 20. It is the number of oscillations divided by the time, right? Oh, no, it's the time divided by the number of oscillations. See, because that's where students go wrong. It is the time divided by the number of oscillations. So you get 3 by 4. And then when you plug all that in, you see how it cancels out, how you can do that without a calculator. Do you see that? Hope you did. So 3 by 4, and when you square it becomes 9 by 16. So you see that 16 goes to the top and 9 is down here. That 9 gets canceled out with this, and then you have the 16s cancel out, you have the pi squared cancel out, and you're left with, even the powers cancel out. And you get 4 ampere meter squared. That's why you can do these problems without using a calculator, because the numbers and values given are in such a way that you can cancel them out. So here the focus is not on testing your mathematical ability, it is on your conceptual understanding of physics and the remembrance of the formulas to be applied in each case. Okay, that's what makes it tough. So number 6, identify the correctly matched pair. So this is about diamagnetic, paramagnetic, and ferromagnetic materials. And you have to know that most of the elements in the periodic table are diamagnetic. Okay, so they're diamagnetic. There are only a couple, maybe 2 or 3, that are ferromagnetic. That's iron, cobalt, and nickel. These 3, iron, cobalt, and nickel, are ferromagnetic. And ferromagnetic means they are strongly attracted by magnets. Diamagnetic means they are repelled by magnets. Between the two, you have paramagnetic. Paramagnetic materials are feebly attracted by magnets. They're not attracted like iron, but they are feebly attracted. So here really you have to know what materials are what, okay? There's nothing else. And from this one, the answer is sodium, and sodium is paramagnetic. You just got to know that. But I'm going to give you a list of materials so you can see and just go over and have an idea of what. Most of them, like I said, are diamagnetic. That includes gold, silver, that copper, all these are diamagnetic. So, but in this case, the answer is sodium, which is paramagnetic, because all of those others are wrong. Like, for example, alnico. Alnico is an alloy of aluminum, nickel, and cobalt, and that's a strong ferromagnetic material, not soft ferromagnetic. So it's hard ferromagnetic. On the other hand, copper is diamagnetic, so not hard ferromagnetic. So you look at that, so that's not matched correctly. And permanent magnets are made of alnico. Permanent magnets are made of alnico. And so I'm going to give you a list, and from there you'll have to remember that, okay? Number 7, if the radius of the Ds of a cyclotron, now what is a cyclotron? It's a particle accelerator. And you have 2 Ds, yeah, remember that? If the radius of the Ds of a cyclotron is little r, then the kinetic energy of a proton of mass m accelerated by the cyclotron at an oscillating frequency is. So what are we looking for? Kinetic energy. What is the fundamental formula for kinetic energy? 1/2 times mass times velocity squared. Yeah, you can start with that. But we should also look at the answers, and in the answers you only need mass, frequency, and radius. You see that? Mass, nu, frequency, and r, radius. So if you write it as 1/2 mv squared, you have velocity there, so that means you have to substitute for velocity in terms of frequency. So let me show you how to do that. So you know that in a cyclotron, the centripetal force mv squared by r is provided by the force on the charged particle, which is qvb. So that's why the centripetal force mv squared by r is qvb, from where you get a formula for velocity. It's qbr by m. So at least now we can substitute for velocity. And then again, kinetic energy is 1/2 mv squared, and we have to bring frequency into the picture. Now, what is frequency? Frequency is the number of oscillations or rotations in this case in 1 second, right? How do we find that? Time, remember, time is distance by velocity, and frequency is the reciprocal of that. So here you can see distance is 2 pi r. Isn't that the distance in one rotation? 2 pi r by velocity would have given you time period. But if you take the reciprocal, you will get the frequency. That's why I flipped it. So frequency is v by 2 pi r, but we already know that velocity is qbr by m. So substitute, you get that, the radius will get cancelled out. That means qb is 2 pi m nu. And that means velocity is 2 pi m nu r by m. So velocity is 2 pi nu r. See what I did? I wanted to get velocity in terms of frequency and radius, because I know that the final answer only has frequency, radius, and mass. So now I can substitute it back into this. Velocity squared, so you got to square all of these quantities. So that's why we got 4 pi squared, nu squared, r squared. And then when you cancel 4 by 2, you get 2. So the answer is 2 pi squared m nu squared r squared. Oh my goodness. So you had to do all this in how many minutes? 1 minute. No kidding. No kidding. You really have to know what you're doing in order to finish 120 questions. Let me tell you that almost nobody finishes 120 questions. It's about how many can do more number of questions in the fastest time. So that's what this entrance exam is about. Okay. Number 8. Let's go. Okay. If a magnetic dipole of moment m situated in the direction of magnetic field B is rotated by 180 degrees, then the amount of work done is. So you have a dipole. When a dipole is kept in a magnetic field, if you try to twist it, there will be a torque that acts on the dipole, tending to bring it back in the direction of the magnetic field. So here, initially you have the dipole situated in the direction of the magnetic field, but what you're doing is you're rotating it through 180 degrees and putting it exactly opposite to what it would like to be in. That's like lifting an object from the ground and keeping it at a height. You're doing work against the gravitational field. So you want the gravitational field wants the object to be on the ground, you're moving it opposite. Similarly, you want this magnet wants to, or let me say the magnetic field wants to keep the magnet aligned in the direction of the magnetic field. But what did we do? We twisted it and took it exactly opposite, so we have to do work. And the formula for work and rotation is always torque multiplied by angle, remember? But I'm going to give you a direct formula here, which you got to remember. Initial angle is 0 degrees, the final angle is 180, and the work done is given by mb cosine theta I minus cosine theta f. Now, remember in one of these previous problems, I used mu as the magnetic moment, mu. That's a standard symbol, but this question says magnetic moment is caps m, so I'm using m. Okay, the mu is the same as the m here. So now substitute into that, and you would get cosine of 0 is 1, and cosine of 180 degrees is negative 1. And so 1 minus 1 makes 2, therefore it's 2mb. That's the answer. Well, of course it cannot be 0. You're doing work, it cannot be 0, and you can't get the others. So the answer is 2mb. Right? Shall we move on to number 9? This is about induced EMF. You know what induced EMF is? When the magnetic field associated with an electrical circuit changes, an EMF is induced in it. Okay, it's like you have a coil and you bring a magnet, move it through the coil, there is going to be an EMF induced in the coil. Why? Because the magnetic field associated with the coil changed as you moved the magnet. So there are two laws, Faraday's law and Lenz's law. According to Lenz's law, the direction of the induced EMF is always such as to oppose whatever is causing it. So if it's the movement of the magnet that is causing it and the north pole of the magnet is coming down, immediately the induced EMF will make the coil a magnet with the top being the north pole. You got that? The magnet is coming down with the north pole at the bottom, and the coil becomes a magnet with the north pole on the top. Idea? Two north poles repel each other. So you see that the incoming magnet is what is producing the magnetic induced EMF, but the induced EMF is trying to oppose the motion of the magnet. So that's Lenz's law. So the polarity of the induced EMF is given by Lenz's law. You know, the other laws, Ampere's circuit law is different, Bayer and Sauer's law is different. I know you need to know all of these. Fleming's left and right hand rules, they give you the direction of the induced EMF when a conductor is moving through a magnetic field. The other one is the direction of the force acting on a charge moving through a magnetic field. So all those are different, but you need to know all of those. But you need to know that Lenz's law is the correct answer in this case. I don't think I'm making it easier for you, right? Okay. So the direction of the induced EMF is given by Lenz's law. Just trying to catch my breath, speaking so fast. But jokes apart, you need to know about the other laws too, okay? Well, I can state all those laws, but I'm not going to do that here. So in this case, you just need to know the direction of the induced EMF is always opposite to the cause that produces it. Well, in an LCR series circuit at resonance, and I saw A, and I said, well, that's the answer. Because at resonance, the current and voltage are in phase. That is the answer. Now B, the impedance is maximum? No. In an LCR at resonance, the impedance is minimum. The current is maximum. So B and C gone. Quality factor. Actually, quality factor, there are many formulas. One of them is omega L by R. So quality factor depends on the resistance. This one says quality factor is independent, so that's wrong. Now E is exactly opposite to A. It says current leads the voltage by pi by 2. That's wrong. The current and voltage are in phase. So that is the frequency response curve. At the resonant frequency, you see the current is maximum. Okay, so I'm trying to write that there. If the current is maximum by Ohm's law, the impedance must be minimum. And actually, impedance is given by this, square root R squared plus XL minus XC whole squared. And at resonance, XL, the reactances become equal. The inductive reactance becomes equal to the capacitive reactance. They cancel out. That's why the impedance is just the resistance, which is a minimum. You can see that this is two terms here. This term becomes 0 because XL becomes equal to XC. And if this becomes 0, then Z is, of course, at its minimum value. Okay? Right? I hope you got that. A conducting ring of radius 1 meter kept in a uniform magnetic field of 0.01 Tesla rotates uniformly with an angular velocity 100 radians per second with its axis of rotation perpendicular to B. Oh, so it's a ring, so something like that. Its axis of rotation is perpendicular to B. So if you have this as the magnetic field, the axis is something like this. So it's rotating like that. You see that? The ring is rotating like that. Okay? And the maximum induced EMF, again, this is the principle of a generator. Because when you have a coil rotating in a magnetic field, you get induced EMF. And the maximum induced EMF is given by NBA omega. NBA omega. So the maximum induced EMF is NBA omega. N is the number of turns in the coil. In this case, it's just a ring. So there's only one loop, one ring, one loop. B is the magnetic field strength given. A is the area of cross section. And we know for a circle, area of cross section is pi r squared. The radius is given, so pi r squared, easy. Omega is given, 100 radians per second, proper units. So now all you got to do is substitute all of that and you get the answer. 0.01 times 100 cancels out. So you get pi volt. That's it. Pi volt is the maximum induced EMF. So we had just to remember the formula for the maximum induced EMF, right? A step-down transformer increases the input current should be from 4 ampere to 24 ampere at the secondary. So you have 4 amperes at the primary, 24 amperes at the secondary. If the number of turns in the primary coil is 330, then what's the number of turns in the secondary coil? Two formulas here important, which I'm going to write down and set them equal to each other. First of all, IP, I'm writing the given terms first. IP is 4 ampere. I already told you, didn't I? IS is 24. NP is 330. And NS is what we are trying to find. All right. Now, here are the two formulas. Vs by Vp is Ns by Np, which is equal to Ip by Is. You notice? Notice the inverse there. Okay? Here it is direct, but here it's inverse. So remember that? So we have this. This is what we're going to use. When you use that, make Ns the subject and rearrange. You get that. 4 by 24 is 6, of course. 330 divided by 6 is 55. So you get 55 as the answer. In a plane electromagnetic wave, the electric field of amplitude 1 volt per meter varies with time in free space. The average energy density of magnetic field is. This is a good question. It's about a plane electromagnetic wave. The electric field amplitude means the maximum value of electric field is given. And we are asked to find the average energy density of the magnetic field. You see that? You're given the maximum value of the electric field, but you're asked to find the average energy density of the magnetic field. How is that possible? Because you have to know that in a plane electromagnetic wave, the average energy density of the magnetic field is exactly the same as the average energy density of the electric field. They both have the same average energy density. If you don't know that, you can't continue here. Okay, now knowing that, mu b is 1 by mu naught times b squared. That's the formula for the average energy density of a magnetic field, mu b, sub b. And then this is the formula for average energy density of an electric field. Yes, you have to know those. 1/2 epsilon naught E squared. Yeah? And you see that I set them both equal to each other? They're equal. So you just find that of the electric field, you will get that of the magnetic, is what I'm trying to say. So epsilon naught is the permittivity of free space. That's 8.85 times 10 to the negative 12. Man, you got to even know the values of the constants. Can you believe it? And then E is 1. So when you do that, it's easy to do 8.85 by 2. It is 4.425, which is rounded to 4.43. And you get 4.43 times 10 to the negative 12. Notice, we calculated the average energy density of what? The electric field. But that's exactly equal to that of the magnetic field. I hope you're getting the idea there. Which one of the following is the property of a monochromatic plane electromagnetic wave in free space? Which one of the following is the property? Now you got to look at each one carefully. Electric and magnetic fields have a phase difference of pi by 2. No. In the electromagnetic wave, they rise and fall together. They are in different planes. One will be in the XY plane, the other will be in the YZ plane, but they rise and fall together. You know what I mean? So that's wrong. The energy contribution of both electric and magnetic fields are equal. I just told you that. That is the answer. Because it's a plane electromagnetic wave. So that's a repeat. Then C, the direction of propagation is in the direction of electric field E. No, it's not. It's the resultant. So if you have the electric and the magnetic, the direction of propagation is along the resultant. So C is wrong. Pressure exerted by the wave is the product of energy density and speed of the wave. No, it's wrong. Because the pressure is exactly equal to the energy density. Okay. Speed of the wave is B by E. You know, you could get caught on that. They put it backwards. The speed of the wave is actually E by B. See that? It's E by B. But what's given is what? B by E, which is wrong. That's why the answer is B.